So we showed that for every state J, this nu J is finite. Now we will show that for every state J, this nu J is positive. The proof would be very similar. So now we can go a bit faster. Now, again, we'll use the fact that nu of I is 1. Now, we'll use the irreducibility in the sense that we'll use it for the conclusion that I leads to J. So I is the specific state and J is our general state. The last time we used J leads to I, now we'll use I leads to J. We are actually going to, therefore, we are actually going to use the full strength of the irreducibility because J is an arbitrary state. So essentially what we are using is that I, the specific state I communicates with each state J. Okay, that's what we are using. We are using the full strength of irreducibility here. So since I leads to J, there of course will exist an integer n such that Pijn is positive. Again, nu transpose P equals nu transpose implies nu transpose P power n is nu transpose, just like before. So therefore, nu J would be this sum of nu K P K J n. This is of course bigger than or equal to when you just specify K equal to I, which is nu I times Pij n. Nu I is 1, so let's use it, and Pij n is something positive. So therefore, what we showed is that nu J is positive for all J. Again, if you go through this proof, you realize that it's not important that nu I is 1. As long as nu I is positive, this proof will go through. In fact, it doesn't have to be the specific I, this specific state I for which nu I has to be positive for this proof to go through. As long as nu I is positive for some I, for some state I, along with the irreducibility will give you that all the nu J's are positive. So that's the strength of irreducibility. And as I said, we are using the full strength of irreducibility in the sense that we are using that this fixed state I leads to, communicates with actually. In this case, it leads to any state J, but the previous part, we use that J leads to I. So therefore, we are using the full strength of irreducibility. Okay, so we have just shown that for all J in S, therefore, nu J is strictly between 0 and infinity. Again, I would like to stress this thing because we are going to use it soon. So we use the fact in the proof that nu I equals 1, where I is our specific state. But the proof would actually go through as long as there exists some state L for which nu L is strictly between 0 and infinity. If that is the case, then the proof, from one state we can go to all states by using irreducibility. And basically the way we will go is, if you go through the, let's quickly go through is, this particular proof where we prove that each nu J is finite. Here instead of starting with I, we'll start with L. And then we'll use the fact that nu of L is finite to show that nu J is finite. Okay? Here instead of 1, you will have nu L by Pjl. Okay? And then irreducibility, of course, we'll be using. Similarly, on the other side, you don't need this, your favorite state I, to have nu I equal to 1. You just need one state L for which nu of L is positive, and that will give you that each nu J will be positive. Okay? So that's the strength of irreducibility, as I said. Okay, so why do I bother about that? It will be clear soon. Okay, now suppose mu is another invariant measure. This basically means that each mu J is a non-negative real number such that mu transpose P is mu transpose. Okay, it doesn't have to be that the mu J's will sum up to 1. They all have to be non-negative real numbers. So in particular, they should be finite, okay, by definition. To show that there exists a scalar C, a non-negative scalar C such that mu j equals C times mu j for all j in S. Why non-negative? Because mu j's and mu j's are all non-negative. So therefore, the scalar has to be non-negative. So basically, this will show that any invariant measure is a scalar multiple of the invariant measure that we have constructed. So we have already constructed a new invariant measure. If mu j equals 0 for all j, then we are done because C equal to 0 will do the job. But that's a boring case. Let's not consider that case. The more interesting case would be when this is not the case, which means there is this one state L for which mu of L is strictly positive. And of course, by definition of invariant measure, that particular mu of L also has to be finite because that means if mu is an invariant measure, it means all of these are finite and non-negative real numbers. Therefore, there will be some state L for which mu L is strictly going to be between 0 and infinity. Now, because of the observation that we made in the previous slide, if you follow the same proof and irreducibility of the Markov chain, it follows that mu j, each mu j, okay, is strictly between 0 and infinity. So each mu j is a positive real number and finite as well. Without loss of generality, we can assume that mu y equal to nu y, this should be nu y, okay, equal to 1. Why? So this should be nu y. Okay, nu y is already 1, we know. Now we can assume without loss of generality that mu y is 1. Why? Because each mu j is positive and finite. In particular, mu y is also positive and finite. If it is not 1, we'll just divide the entire invariant measure by mu y. Remember, I is our favorite state, I, that we started with. Okay? So this should be mu y. Okay. So if mu y is not 1, we'll just divide everything by mu y, and that will give us another invariant measure, which will be a scalar multiple of mu, but that will satisfy mu y equal to 1. So that's okay. We can always divide by mu y everything and make sure that mu y is 1. Okay. If needed, we divide by, you scale the entire invariant measure and make sure mu y is 1. We will have to show, if this is the case, then we'll have to show that mu j equals mu j for all j in S. Okay. Since mu y is already equal to nu y, the scalar multiple, now it would mean that the scalar has to be 1. So therefore, we have to show that this is the case. Now, this can be done by showing two inequalities. Mu j is bigger than or equal to nu j, and mu j is less than or equal to nu j. And this proof is slightly tricky. And it uses a certain tricky algebra. It's not incredibly illuminating. It's just you have to use the fact that mu is an invariant measure, and then you have to use slightly tricky algebra. So I'm going to skip this part of the proof. Okay. So I'd ask you to go through this part of the proof from the textbook, these 2 pages. It's slightly long and tedious, and it doesn't give any input in the probabilistic understanding of the Markov chain. And therefore, I've decided to skip this part of the proof. So I ask you to read it yourself. Okay, so this should be nu y, okay? So essentially, we are assuming that mu y and nu y are the same. Okay, so once this is done, the proof is complete in the sense that it will prove that any invariant measure mu is a scalar multiple of this nu that we started with. Okay, so now suppose I is positive recurrent, then we know that the scaled version this normalized version of nu j, pi j is a stationary distribution of the chain. Now, any stationary distribution will also be an invariant measure. Hence, it will be a scalar multiple of nu. Now, note that nu is a scalar multiple of pi. You're dividing by something positive and finite. This is expected return time, which is positive. Return time is at least 1, right? So it's positive, and also is finite because I is assumed to be positive recurrent. So therefore, if something is a scalar multiple of nu, it's also a scalar multiple of pi, because pi itself is a scalar multiple of nu. Okay. So therefore, any stationary distribution is a scalar multiple of pi. Now, if a probability distribution is a scalar multiple of another probability distribution, then they have to be equal. Because after all, a probability distribution sums up to 1. Okay? So all the i's have to sum up to 1. Right? So therefore, the only way two probability distributions can be proportional to each other is when they're equal. The constant has to be 1. The scalar has to be 1. So this shows that the chain in this case, when I is positive recurrent, that is, the chain has a unique stationary distribution. Okay? Because any stationary distribution has to be a scalar multiple of nu, and therefore it has to be a scalar multiple of pi. And then two probability distributions with the one being scalar multiple of the other have to coincide. Therefore, this shows the uniqueness statement in the theorem. So this completes the sketch of the proof. Sketch because there's one part that I left out and I want you to read. Now what we will do is we'll try to see what are the consequences of this theorem. And as you will see, this theorem has actually a lot of important consequences.